Hello, everyone, and welcome to today's Industrial Laser Solutions webcast entitled Laser Measurement Techniques for Beam Control and Materials Processing. This event will be presented by John McCauley and Dick Riley from Ophir Spiricon and is also sponsored by Ophir Spiricon. John McCauley is Midwest Regional Sales Manager for Ophir Spiricon. He joined the company in January 2009. Since 1998, his background has been as an end user of and an applications engineer working with laser marking and engraving systems. He also served in the U.S. Navy as a nuclear qualified machinist mate on fast attack submarines out of Pearl Harbor, Hawaii. Dick Riley is Sales Manager, Mid-Atlantic region for Ophir Spiricon. He's worked for the company since 1998, and prior to that, he was Sales Manager with Vanzetti IR Laser Systems and Product Manager at Belden Corporation. He holds a BS degree from Miami University. Ophir Spiricon provides a complete line of laser instrumentation for manufacturing and materials processing, from beam profiling to power and energy meters. The company holds a number of patents, including UltraCal, the algorithm that helped establish the ISO standard for beam measurement accuracy. The company is also ISO IEC accredited for calibration of laser measurement instruments. Ophir Spiricon is a division of Ophir Photonics, a Newport Corporation brand. This webcast presentation is both live and interactive, so you can feel free to ask questions at any time by typing your questions into the Ask a Question area on your screen and clicking the Submit button. All questions will be answered by email if we run out of time during the Q&A period that follows this webcast. So if you are running pop-up blocking software, please disable it now to view this webcast. And also, it's recommended that you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event, and the email message will be sent to all registrants with a link to the archive. A PDF of the presentation is also available under the Event Resources tab just below the Ask a Question area. You can also access this presentation from the home page at www.industrial-lasers.com. In addition to supporting audiences on the Internet using Adobe Flash and Microsoft Windows Media, Penwell now offers webcast viewing via tablets and smartphones for seamless access to both live and on-demand web presentations. So with that, it gives me great pleasure to introduce John McCauley and Dick Riley from Ophir Spiricon.
Thank you very much, Gail. Appreciate the introduction and your kind words. This is John McCauley out of the Midwest. I'll be starting off today's presentation. I'll pass it off to Dick Riley here momentarily, and we'll go from there. Do want to first of all thank Laser Focus World and Industrial Laser Solutions for the opportunity to speak today. Anytime we're able to interact with laser users and have a session like this, it always seems to be very beneficial for both parties, and certainly want to thank you for the opportunity. Also like to thank everybody who is attending today. It really does say something about you for you to take time out of your busy day to attend a webinar like this. That, you know, it says something about you caring about quality and having consistent laser processes. So you should be commended for taking time out of your day to join us today. We know that you're busy and your time is valuable, and we really do hope that this session is beneficial for you. We do today have a very wide variety of laser users, and there are a wide variety of laser applications that you all work with. So for the most part, this session will be general in nature. Like Gail mentioned, if you do have any specific questions for us, feel free to type them into submit your questions below, or if you want to contact myself or Dick Riley, we'll be more than happy to address those questions offline. wanted to start off by showing this quote by Dr. H. James Harrington. He is an American author, an engineer, an entrepreneur, and a consultant in employee performance measurement. And he said at one point, he said, measurement is the first step that leads to control and eventually to improvement. If you can't measure something, you can't understand it. If you can't understand it, you can't control it. And if you can't control it, you can't improve it. Now, even though he was talking specifically about the measurement and the improvement of employee performance, you could definitely say the same thing about a number of things. For instance, if you want to improve your health, there has to be some benchmarks for measuring whatever and diagnosing whatever problems you might have with your health. And it certainly can be said about material processing with lasers. If you want to have a consistent, improved quality laser performance or laser process, you've got to be able to measure it. You've got to be able to understand it and control it, and you've got to be able to measure it in order to do that. So let's talk about laser beam measurement. What we're going to be talking about today, just in general as an introduction, we're going to be talking about what measurements should be taken on your laser. We're going to talk about the reasons why you should be taking those measurements. We're going to talk about how. We're going to talk about the different technologies that are available for laser measurement. And then finally, we're going to talk about when these laser measurements should be taken. So, laser performance characteristics, what measurements should be taken? First of all, you've got output power energy, and typically this is with material processing. This is the power energy at the workpiece, and I think probably most laser users here are familiar with the concept of taking a power meter or energy meter and measuring your laser at the workpiece. You should be taking the spatial profile, or what's called the beam profile, and we'll talk about what that is. You should be taking caustic measurements, beam waste measurements, or focus spot measurements. And we'll talk about what those measurements consist of as well as the temporal profile or the pulse shape. These are all very valuable pieces of information about your laser when you try to control your laser process, when you try to measure it. Let's just first of all establish a definition of terms. When we talk about output power or energy measurement, how I've defined it is a quantitative measurement in which you direct a beam from a laser into a sensing device, interfacing that device with a meter or a personal computer interface to read the amount of either CW power, average power if you're talking about a pulse laser, or energy per pulse that the laser is producing. You want to know how much stuff your laser is outputting, and you need to be able to measure that measurement. When you talk about spatial profiling, or what's called the beam profile, there are historically a number of different ways to obtain this information about your laser. How I would give a modern-day definition to what the beam profile is a qualitative measurement which uses a device to image a laser beam or a sample of the beam, then interfacing that imaging device with a PC and analyzing that image using beam analysis software. Measuring the beam at different spots in the beam path will give you the overall health of the entire laser system. So where the output power or energy measurement is how much or the quantity of the light hitting your workpiece or your process or your material, the spatial profile is how it is hitting that material that you're processing. What is the overall health of your laser system? When we talk about caustic, beam waste, or focus spot measurement, what we're doing is we are measuring what is happening right at the where the light interfaces with your material. So how I would define beam caustic measurements would be capturing a series of beam profiles through the laser beam's waste, in other words, the area around the laser's focus spot, in order to determine the quality of the laser as it is applied to the process or the material. This is also known as determining the m² value of the laser. So you want to know how well your focused light focuses down to the spot and how it performs at that point that it interfaces with your material. And then finally, the temporal profile or the pulse shape can be defined as using a device such as a fast photodiode interfaced with an oscilloscope or a PC to measure the amount of relative energy in a laser pulse with respect to time. So it's the rise and the fall time of the laser, and you see that that graphic there off to the right, where you can visualize the x-axis being time and the y-axis being relative energy. You can see that that laser pulse, it comes up to a peak, it comes down, levels off, and then drops off. That is how much energy or how the energy is performing with respect to time. Okay. Why should laser measurements be taken? Now, this is a question that I get all the time as a laser measurement expert and a sales engineer of this equipment. You know, John, you've given me pretty pictures of my laser. You've given me these graphs. You've given me these numbers. What am I supposed to do with this laser? And it's a very good question. Now, again, we're talking probably to a number of different types of laser users, and you've got a number of different applications. So how I would answer this question just in general is to ensure a stable, reliable, consistent, and repeatable laser process. Now, that is why we're here today, right? We all want to do our job better. We all want to have quality, consistent, reliable laser processes, and this is the reason, the main general reason why you should be measuring your laser. But just to talk about some specific answers rather to this question. In order to prove a quality laser process, the process must be measured. It comes back to that quote that we opened up with by Dr. James Harrington. If you want to prove that you have a quality laser process, it has to be measured, and because that's the only way that you're going to be able to prove that. All laser systems are made of matter, right? They're all made of stuff. They're made of physical components, and they will degrade over time. So that's another reason why you need to be measuring your laser, because you want to ensure that these laser systems are performing consistently from day to day, and you need to know when you need to take action if they are not. Laser system components sometimes catastrophically fail. Again, they're made of things, they're made of stuff, and fact of the matter is that sometimes these laser components fail. If you don't know what your laser looks like when you do have a quality process, you don't know how to bring your laser back to that quality process if you run into the likely event that you have a system failure on your system. Now, at this point, I'll turn the presentation over to my colleague Dick Riley, who will discuss the value and approach to the use of laser power and energy measurements for a controlled laser process. Dick?
Thank you, John. And thank you all for spending your time this afternoon with us. I'd like to give you a little idea as to the complexity of a topic that I believe is taken with great simplicity when it comes to the proper selection of an energy or a power meter. It tends to be an area that is the last thought of when a laser system has installed, and an area that is given the least amount of attention when it comes to the proper selection, yet it is one of the basic elements necessary in the measurement of that laser's performance, not just in setup purposes, but in process control. Knowing the power, as John said, at the work surface is the only true measurement. This is the only value laser counts. Without knowledge of the power at the work surface, process failure is ensured. You really don't have any idea what is being performed at the work surface, whether it be a cutting or a welding or an ablation process. without knowing what is happening at that point in space. Over time, laser powers don't increase, but they can always drop. Many lasers have internal power sensors, but are located before the delivery optics. So as a result, the information that is displayed on the operator's computer screen, control screen, may or may not have any relationship to what is being performed at the work surface, and therefore measuring it at that location becomes a necessary part of process control. Deterioration will happen due to optical train misalignment, failures of the optics, dirty optics, or just the power supply. But without some way to measure this, and to measure it in such a way that allows you to see this deterioration prior to making defective product, or prior to making product that does not meet specification, is essential to good process control. And that's where a power meter or an energy meter comes in, because it will provide that kind of information as part of a trend analysis if done on a frequent basis, demonstrating that either the laser is stable, maintaining its specification, or it is beginning to deteriorate for some reason that needs to be identified and corrected. Otherwise, at some point soon, the defective product will be caught, and by that time, expenses have started to add up, not just in rework, but maybe having to make the product all over again from scratch. We're going to talk about two kinds of power meters and two kinds of applications. This happens to be a selection of thermal pile or average power sensors that are most often used for CW or continuous wave lasers, used to measure average power. It's a simple application. Put the sensor under the laser, take a reading, you get a measurement in milliwatts, watts, kilowatts, whatever it may be. These can be photodiodes, they can be thermal pile sensors. In any case, what it is doing is taking a measurement over time and giving a measurement in average power. Most thermal piles and even photodiodes will measure power over a matter of hundreds of milliseconds to several seconds before an actual reading is provided. Although thermal piles tend to be less expensive, because they are an averaging feature, which is basic to their design, trends that may be hidden in the actual activity of the laser pulses may not be detected and go undetected until some sort of failure may occur. There's 5 factors in selecting a laser power sensor for a CW laser. One is wavelength. There are average power meters that are very specific in their wavelength selection and are considered wavelength specific, and there's others that are broadband that can be used for a wide range of wavelengths without having to select a specific wavelength at all. Here's a good example of the complexity of an average power thermal pile absorption curve. You can see that these are all different types of discs that may be provided in a thermal pile sensor. Selecting the proper one for the right application is essential because the absorption curves are all over the place, and they're specific to an application, they're specific to a kind of laser. But without understanding and being sensitive to the wavelengths, the incorrect sensor can be selected and the wrong information generated. Another factor in selecting a sensor is the beam diameter. Many times a beam will be placed onto the sensor and it's too small. The power density is too high, and this will damage the sensor. If not immediately, it certainly will over time. In the same way, the beam could be too large. And by doing so, the beam actually washes over the aperture of the sensor, and only a portion of the beam is on the sensor, and the reading is low. So selecting a thermal pile where the active area provides a sufficient amount of area to be covered is necessary. Typically, it's recommended to provide a sensor that will allow you to cover about 75% of the active area and provide a power density rating, which we'll get to in a moment, that is under 60% of its damage threshold. Here's a typical example of a thermopile disc where the beam size was too small. The disc was likely put at the focal point of the beam. The power density was in the kilowatts of power, and the disc was damaged. You can see on the left-hand side where the coating has actually been ablated. The absorption will drop to very low numbers. The readings will go down, and the thermopile will need to be repaired and recalibrated, an expensive process. So using a beam that is too small typically will destroy, if not immediately, will certainly over time damage that detector from reading accurately. Another factor in the laser power sensor measurement selection is the power range needed. What I'm trying to say here is that if you have a range in a sensor, let's say, that measures from 100 milliwatts to 10 watts, just to take an example, and your measurement is in the area of 110 milliwatts, that's not the best sensor selection for that application. You run the risk of taking measurements that, should they drop below 100 milliwatts, begin to run into the noise of the sensor. Typically, most thermopile sensors, the low-end measurement that is accurate and meets the accuracy spec for that sensor is typically about 20 times noise. And as you drop below that low-end measurement value, in this case 100 milliwatts, the failure and the influence of noise increases at an increasing rate. So in the same way, if you have a 100 milliwatt to a 10 watt scale and you select a sensor that for your laser that you need to read 9.5 watts or 9.8 watts, you run the risk of going over 10 watts, in which case, again, damage to the sensor may not be, may occur, and this will cause damage as well. So try to select a sensor where the range will fall in the middle of what you need to measure. This will ensure that you get full accuracies for the range that is necessary in your application. Another factor is the power density. Power density many times is overlooked. Power density is what damaged those discs you saw in the earlier slides. The power density was just too high. The amount of power in a spot exceeded the capability and the design of that specification. In this example, we have a 10 watt laser. We've got a 4 millimeter beam. Power density equation is average power divided by pi r squared times 100. And for this application, it's 70 watts per centimeter squared. That's a pretty low value. And in our case, that's 50 different sensors will meet that criteria very easily. However, if by chance that disc and that absorber is placed at the focal point, and let's say the focal point in this case happens to be 500 microns, half a millimeter. Now we've got 10 watts, and that'll give us a power density of 5.09 kilowatts per centimeter squared. That's absolute damage, and this can be the impact of a focus beam, and that disc will get damaged at that location. And if done frequently enough, that disc will have to be replaced and recalibrated. A process that is expensive and can easily be avoided by considering the power density specification for the sensor and the application and the beam size of your laser. Another factor that is many times not considered is exposure duration. For short exposures, snapshot applications, daily measurements, 1 to 2 minutes at most likely, air-cooled sensors, which many of the thermopiles are up to 150 watts, are fine. There are also fan-cooled sensors that operate from 150 watts to even up to 500 watts, which are great to use. Response time can be anywhere from less than a second to 2.5 seconds, but great for short-term exposures, daily process control activity. Prolonged exposure, however, is a different issue to deal with. This may be testing for stability, life testing of a laser. It may be other applications where it's important to track laser stability with regard to the beam pointing capability of the laser. And in this case, air-cooled sensors are not recommended. Fan-cooled sensors are really necessary, 150 watts up to 500 watts, and there's water-cooled sensors from 250 watts up to 30 kilowatts. In either case, having a cooling capability to that sensor is essential, because otherwise the detector has no way to dissipate the heat that is building up in that sensor as a function of that particular application. So considering the exposure duration of a sensor is important, depending upon how you plan to use it. Here's a typical trend analysis on a 5 kilowatt laser, just to give you an idea how this could be used in a process environment using some typical software. Over a matter of literally half a second, or half a minute rather, you can see that the beam power actually ramps up and then decreases a bit before it actually levels out at 4.8 kilowatts. And the value of this information is that it provides the operator and process control management with a template to know that as long as this is the same trace we're getting day after day and process after process, we've got a laser that is holding its own and is not going to give us concern that any deterioration is in process. Another factor in sensors, and it deals with the kind of laser we're dealing with, are energy measurement sensors. These are pyroelectrics. These measure energy per pulse, typically for pulse lasers that are operating under 25 kilohertz. We use an energy sensor, and these are pyroelectric sensors that produce generally a volt per joule type of signal. In this application, again, there's not just 5, but there's 7 different factors to deal with. As before, wavelength is important. There are pyroelectric sensors that are very specific to wavelength. There are others that can be used across the spectrum quite easily. This is a typical example where you have wavelength across the x-axis, and you'll see that only 3 of the few that we list here are really considered broadband sensors. Others are very specific to specific categories of wavelengths or limited altogether to 3 microns or less. So selecting the right wavelength category is important. Otherwise, the measurements will be inaccurate and inappropriate. Another factor is beam diameter. Just as before, too small, we're going to damage the crystal. Too large, we're going to get a reading that is not even representative of what the laser is putting out. Same factor as before. Energy range needed. This is similar as before. Energy range needs to be within the range of the sensor selected. Get it in the middle. Don't select on the high end or the low end. Pyroelectric sensors tend to be even more sensitive to measuring on the low end of dropping below the low end value of reading inaccurately, and even on the high end you run the problem of damage. So on the low end it's accuracy issues, on the high end it can be damage issues. So staying in the middle of the range of the meter of the sensor you've selected for the laser you have is equally important. This is an area that is also not always considered as one of the key factors, is the pulse rate of the laser. Most pyroelectric energy sensors can measure pulse-to-pulse energy for 25 kilohertz and less. You can also use an average power meter, but energy sensor is far more informative. As I mentioned in the earlier on, if you are working with a pulse laser and you have the choice, an energy sensor is far more informative to process control management than an average power sensor. Energy sensor will provide pulse-to-pulse stability. You'll get an average, a mean, a standard deviation value that is accurately quantified, except rejects limits to be set on each one of these parameters that will allow for the detection of possible deterioration, pulse-to-pulse stability beginning to deteriorate and the variance starts to increase, that by using an average power meter you would never see. Not until it becomes much more catastrophic. And by then, it's likely you're making product that's not acceptable. Greater than 25 kilohertz, generally There are very few energy sensors that can handle that with providing a complete pulse-to-pulse information. So most often, an average power sensor is used for 25 kilohertz and above. This is an example of the pyroelectric sensors dealing with the pulse rate. Again, you can see there's only two that really go out to 25 kilohertz. There's several of them that may go out to 10 kilohertz, and there's a variety that in between all the way down to 20. Typically, the 25 kilohertz and up in that range are all dealing with very low energies, generally microjoules or millijoules at most. The fifth factor in considering an energy sensor is the pulse width, the length of the pulse. Most pyroelectric sensors can handle pulses from femtoseconds to milliseconds. There's some limitations, some on the higher end, some on the shorter end, but generally that range is pretty likely. On the other hand, if you get into an application, possibly welding, where the laser is using an extremely long pulse width, maybe tens of milliseconds, it's likely that most pyroelectric sensors cannot integrate energy over that period of time, and an average power meter is going to have to be used. Another factor is energy density. Unlike the thermopile we were talking about for average power, for the energy sensors, the pyroelectrics, we have energy density, joules per centimeter squared. We have the same situation to deal with, a similar kind of formula. Here's the case where we have a 100 millijoule laser. We've got a diameter of 4 millimeters. In this application, the energy density comes out at 790 millijoules per centimeter squared. Pretty much a low value. Only 5 out of 12 sensors are typically possible in a selection when you look at this, and that's not unusual. So it's understanding that calculation or using your routine, or there's several routines online where this information can be calculated for you, is important to be conducted to ensure that the beam size and the energy you're running is suitable and matched to the specification of your sensor. Otherwise, if not immediately, certainly over time, you will damage the sensor, your readings will become inaccurate, and you will be dissatisfied with the performance of that product. Another factor, and this one is almost always overlooked when it comes to an energy pyroelectric sensor, and that's power density of the beam. Why do I have to worry about power density when I'm dealing with an energy sensor? I've already figured out the energy density of that sensor, and it fits. Well, power density is an important issue as well, and power density is nothing more than using that basic formula, energy times time is power. So most pyroelectrics are limited. They're limited in their heat sinking capability. They're generally low power density. They typically don't have fans. Very seldom do they have water cooling capability. And most pyroelectric sensors can only handle an average power limit of maybe 40 watts of power. So typically, pyroelectric sensors are low power measurement devices when calculating that particular element in the laser. Same formula as average power before, and one where it's important to be able to satisfy both conditions, one being the energy density of the specification for the sensor, but also the power density needs to be satisfied as well. If one or the other is satisfied and the other is not, it won't work. And it must be considered, and it's part of the equation in looking at the proper selection for process control of energy measurement. This is a typical slide of a pulse-to-pulse application where an operator has taken a template of pulses, overlaid it on the previous measurements, and is now taking some comparative data as to how uniform the laser is today versus it was the previous time being measured. And this allows for the operator to be able to measure the process by the numbers and provide a clear indication as to whether the laser is holding its own or something is beginning to change and needs to be addressed, or is a situation where they can immediately go into conducting their experiment or making their product because the laser is exactly doing what it should. So just to cover this section for a moment, energy and power measurement is a critical process of process control. Determining the correct sensor is essential. Without that, then feeding information into beam profiling, you're giving it inaccurate data. Setting up a routine to take frequent measurements. In some cases, we have applications where measurements are taken daily because of the critical nature of the process. Some of the processes are covered by FDA requirements and need to be documented on a regular basis. Other applications, they only perform this kind of measurement on a weekly or even a monthly basis to ensure that the process is stable. Establish a baseline of acceptance. With this kind of quantitative data, an accept-reject limit, a min-max level, if you will, can be set on any one of these parameters, allowing for a trend analysis to be established and monitored with ease and without great effort to track the performance of the laser, and knowing that laser is maintaining its performance to your specification. Track the trends of the measurement. And this all comes down to the final statement. Process control and being able to take power and energy measurements allow you to detect change before defects are produced. And that's the value and that's the goal of process control. Without it, the only way you're going to detect these changes is by a product that's been produced in whatever stage, and that product does not meet your specification. And that's what process control avoids. For a controlled process, the accurate measurement of the laser's output power is only half the equation. The measurement of the laser beam, its size, its shape, the distribution of its intensity is equally important. And only if measured properly and accurately can it be controlled. John McCullough will now discuss in more detail laser beam measurement for a controlled process. John?
Thank you, Dick. Let's talk about the different technologies that are available for profiling your beam or getting that not only the quantitative measurement that Dick talked about, how much laser power output your laser is giving, but more characterization, further characterization of your laser beam with respect to how it is performing. Camera-based beam profiling is probably the most widely used method of obtaining a beam profile, not only of your raw beam, but of your focus spot as well. Camera-based beam profiling can be described as by the use of attenuation device, the laser is sampled down to a lower power level that can be measured. For measuring beam size, beam shape, spatial energy distribution, beam wandering, etc. And these are all ways of measuring your, or these are all calculations that are given to you by measuring your beam profile. The camera-based beam profile is also very commonly used for focus spot measurements. If you look at the system down in the lower right-hand corner, this is a system that's produced by Spiricon. It's a camera-based profiler with a beam attenuation device that sits on the front end of the camera. It's called the LBS 300, and what that does is it samples the beam down to an acceptable level. There are neutral density filters in front of the camera to even bring the power level down even more, and then by that point the signal is usable, a usable signal to analyze by the camera. Let's see. This is an example of the software that comes with the Spiricon Beam Profiler. You see the 3D view, you see the 2D view, and then you also see 1D profiles all within the same software, as well as the different calculations that are being made in the upper left-hand corner. Another method that's used with respect to industrial lasers, specifically multi-kilowatt lasers, either CO2 or fiber lasers, is a rotating pinhole method. Small pinhole is presented to the beam, in this case the focus spot, allowing for a small portion of the beam to be detected at a time. Data points are then used to compile the image of the beam. And this particular product is made by Primus, and it's a nice device because you can put it right at the focus spot, and you can move it up and down on a chassis, and then the result is this image that you see off to the right here. Different beam profiles right around the focus spot or through the caustic. So it will give you number one, it'll give you a beam profile, it'll give you the caustic measurement, and it'll also give you the m² value of your beam if you want to know what's going on right around your focus spot. This is an example of the Primus software that comes with that. You see the caustic measurement, you see a beam profile off to the right, as well as all the different calculations that are being made as well. Another useful device for industrial lasers is a spinning wand technique. This is another device that's made by Spiricon. In this case, a spinning wand or a mirror samples a small percentage of the beam by spinning around at a high rate. It uses that signal to sample the collimated beam, and it sends it to an imaging device to beam analysis software to be analyzed. And this is really used for measuring the spatial intensity and the beam size and the shape of unfocused CO2 lasers, so laser cutting systems, laser welding systems that are CO2 based. I want to talk real briefly about all-in-one systems, and here's an example or a picture of a beam being analyzed by an all-in-one system. At the top there you see the laser delivery head, and it's attached to a robot in this case. In this case it's a Laser Mechanisms fiber cut processing head. And what that's doing is it's focusing the beam down to that Primus unit that I showed a couple slides earlier. It's the focus monitor. And then the majority of the beam is passing through that focus monitor into the Primus PM48 water-cooled power meter. So you're getting your beam waste measurement, your focus spot measurement, your m² measurement, as well as a laser power measurement at the same time. This is another all-in-one system. This particular system is made by Ophir and Spiricon. It is the camera-based system that I showed you a couple slides earlier. You see off to the right there. It is attached to the beam attenuator. It's the LBS300. Most of the beam is passing through that attenuator, and in this case it's being captured by a thermopile sensor. This particular welding system is a single pulse welding system, so it's measuring the energy per pulse from the thermopile. It's measuring the focus spot size and the focus spot shape and taking that analysis. And then off to the southwest in the picture there, you see a fast photodiode, and what that is doing is collecting the light to give a temporal pulse shape measurement. So you have the energy per pulse, you've got the focus spot measurement, and you have the temporal pulse measurement all in one system. Here is another system that's made by Ophir and Spiricon. It's called the Beam Cube. It's basically, if I could back up one slide here, it's basically all of these components: the camera, the attenuator, the fast photodiode, and a thermopile sensor, and it's all in. There we go. It's all in one system. So it's a beam analyzer with an internal thermopile sensor, beam profiling camera, and a fast photodiode. It's kind of a nice system because you can put it right underneath your processing head and start to take measurements fairly easily using that method. Okay, so we talked about how we can take these measurements. We talked about why we should. Another question that we as sales engineers get is, when should these measurements be taken? And again, we're talking to a number of different users today, so these might not cover what all you're measuring, but I did want to give some general guidelines or some suggestions on when you should be taking measurements on your laser. Laser systems development and manufacturing to ensure the highest quality laser supply. Now we have, as a company, we've got a number of different laser manufacturers and OEMs that use our products to measure the power, to measure the beam profile, and they will tell you that it's essential to do that just for the specific reason of for them to be able to confidently say to their customers that they are providing the highest quality laser system that they can possibly supply to them. So it's very important on the front end of laser systems development. Application development. What does the laser profile look when the process is acceptable? Now, more than likely, an application is developed on one laser system, and it's moved to another system for when it's put into its production environment. Now, and normally those two laser systems are going to either be the same but two different lasers, or they might even be two completely different laser systems. You need to know what your laser looks like and how it is performing at the application development stage in order to know that your process is running the way it should be when you do transfer that process or that application over to the production laser. System runoff or factory acceptance test. This is to ensure that the laser is performing the same as during the application development. That application is going to be transferred to another laser. It's going to be integrated into a system, and you as an end user, as a customer, you need to know that the system that you are being provided by the integrator or the systems integrator or the laser OEM is meeting your specifications and is performing the way that it was advertised or the way it was running at the application's development stage. Oops. Sorry about that. System delivery or system movement. Anytime you move a laser system, whether it be upon delivery or moving it within your facility, you do run the risk of having those components inside the laser system change. They could shift, they could break. Anytime that you do a system delivery or a system movement, it really is a good idea to take a set of laser measurements before the move, take those same measurements after the move just to make sure that your laser process or your laser performance is remaining consistent before and after the move. Process validation. When you move or copy a process from one system to another. I've got an example of this. A few months ago, I met with a customer of mine who was enjoying some growth, and they were taking in more orders from their current customers. They were taking on new customers, and as a result, they maxed out the use of their current laser, which is great. It's a good problem to have. But that allowed them to purchase an identical laser system. So they approached the laser OEM. They say that we need laser system X. They delivered laser system X, and they transferred over the process parameters from laser 1 to laser 2. Everything should be fine, right? Shortly after they started producing parts, they found out that the welds were failing on laser system 2. Well, how could that be? If it's the same laser system, same process parameters, how can one laser be producing good parts and another laser be producing bad parts? That's when they called me in. We took a set of measurements. We took some beam profiles and found out that the laser number 2 was performing completely different than laser number 1. We had some ellipticity in the beam. We had some more intensity as far as the output power. And bottom line is, no two laser systems are created equal, right? So you need to know when you're moving or copying a process from one system to another that those two lasers are performing the same. Batch validation. Through laser measurement, this is really the only proof to your customer that the laser is remaining consistent during the process of a batch of parts. So you take a set of laser measurements before a batch run, you take them after the batch run, you compare them, make sure that the measurements match up, and you can confidently tell your customers that the laser remained consistent through the processing of those that batch of parts. And of course, anytime you do any laser maintenance, any component changes, whether it be optics or lamps or fibers or any other bellows or whatever else, mirrors, any troubleshooting that you might have to do with your laser system to bring it back to normal, and then any laser process modification that you might have to go through. Any time that you change something on the laser, you really do need to make sure that you have brought your laser system back to where it needs to be performing. Okay. So just in summary of what we've talked about today as far as laser beam measurement in material processing, we talked about what measurements should be taken. We talked about taking laser power energy measurements, the laser beam profile, the focus spot measurements, beam waste measurements, and also pulse shape, all very important to measure with respect to the laser process. Why should laser measurements be taken? We talked about that. To ensure stable, reliable, consistent, and repeatable laser processes. That's all. That's why we're here. That's why we're trying to improve our processes, is because we want all these things in our laser process when we process materials. What technologies are available for laser measurement? We talked about that. Output power and energy measurement systems, beam profiling systems, caustic beam waste measurement systems, and then we talked about all-in-one measurement systems as well. And then when should the laser measurements be taken? You should be taken during the laser manufacturing R&D, during the application development, during the system integration, during the process validation, batch validation, and also in laser measurement. So that concludes our portion. So at this point, I'm going to hand it back over to Gail.
Okay, great. Thank you. And this is time now for our question and answer period. We have about a little less than 10 minutes for questions, and I see there are a number that have been submitted. So John and Dick, if you'd like to select a few questions and go from there.
John, do you want to take that first question?
Question number 8?
Yes.
Okay, so the question is, for laser power measurement, when do I select an energy sensor over an average power sensor? And I think Dick really did a good job at answering that question, but an average power sensor, it basically depends on a couple things. It depends on the laser and how what its characteristics are, and also what your process is. So what I normally tell my customers is that if you've got a repetitive pulse laser over a certain value of what your rep rate is, I'll tell them that an average power measurement is acceptable. Or if you have a continuous wave laser, you want to measure the power as well. If you have a single pulse laser or a repetitive pulse laser below a certain value in repetition rate, that's usually when I recommend an energy sensor or a pyroelectric sensor for those types of applications. So very good question. Thank you.
I think if I could add to that, John, it's I have strong feelings about using an energy sensor. Anytime you've got a pulsed application below 25 kilohertz, typically, if you have the choice of with a pulse laser of taking energy measurements, that value, that information is so much more informative than average power, which is an alternative. But an energy sensor gives you that raw data of, as I mentioned, of the heartbeat of that laser, which no other type of sensor can provide. And I believe that in critical applications and where a pulse laser is being used, an energy sensor is a very valuable tool, but not the only tool, of course. But when that situation exists, I think an energy sensor can be the right selection. Let me take that second question, John. Once I know which type of sensor to use, how do I go about selecting the right model? This basically goes through some of the items I talked about earlier, that once we know that we're going to we have a CW laser, and really it just gets back to, if it's a CW laser, then I just need to know the wavelength, the beam size, and the average power. It's that simple. If I really want to, if I've decided I have a pulse laser and I really need to do energy, then I've got to deal with those 5 elements: the beam size, the wavelength, the energy, the pulse rate, and the pulse width. If there are sources on our website that provide assistance in selecting that kind of sensor and does all those calculations, some of which I showed and discussed earlier today, to make it easy for you. Without that, then sorting through the individual specifications to get the right sensor that's going to work needs to be done. And to be done properly, then you've got the right fit.
Another question came in. It says, where in the laser beam do I position the sensor? This is a really good question and something that throws people off from time to time, as Dick kind of talked about in his presentation. You've got the amount of power in a beam, and you've got the beam. If you can picture it, you can picture a funnel, this beam focusing down to a spot and then diverging again or expanding again. The amount of power really is the same throughout the beam. You've got so much power that it's outputting. What is changing, obviously, is the diameter of the beam. So the amount of power, even though the amount of power is the same, what's known as the power density, or how much power is concentrated down into that, the size of the beam is going to change throughout the waist. Dick showed those pictures of the sensors that were affected by a focused beam. So basically how I would answer that question is, if you expand the beam as large as you can without overfilling the aperture, that's really where you need to be taking your power measurements. Dick talked about overfilling the aperture, and if you think about it, if the light is spilling over the disc, onto the sensor face or onto the floor even, you're not collecting all of the light. So collect all of the light, but don't focus the beam down to a point that's going to damage your sensor. Those are really the general rule of thumb. Usually what I tell my customers is about, if you can put it to where the beam size is about 3/4 of the size of the disc, that's usually a pretty good spot to take your measurement.
Another question that came in is, why should I measure the laser power when the laser control panel already displays this value? That's the reason to measure at the work surface, is because it is displayed on the computer for the laser. And very seldom, in my experience, does the value displayed on the control panel match the output power at the work surface. I did an application just recently where there was as much as 11% difference between what the operator saw on his screen coming from the internal power meter versus what the power meter showed at the work surface, in which case he was in essence underpowering his application by 11% and had no clue of that. Now, I was obviously just there for the day, so I don't know if that was an event that was changing over time or whether it was static. But in any case, they felt they needed to go back then and start to reevaluate some of their product to be sure it was made properly to specification. So the likelihood that the measurement on the screen and what's shown at the work surface match is only by chance, in my opinion, in my experience. The more important thing is if the display shows X and the work surface shows Y, if that ratio is constant, then the laser becomes stable, and that's the kind of measurement ratio that we look to provide to the customer.
I've had the same experience in showing our products to customers as well. Usually the OEM will set, usually, I say usually, but it really differs from manufacturer to manufacturer. But usually what they'll do is they'll sample the beam within a resonator and calibrate that value, which is fine. It gives a good indication of how the resonator is working, but it's still not taking into account the rest of the delivery system, which there are losses. There's, up to 1% loss, at every turning mirror, for instance. So by the time the laser goes through all these turning mirrors, through a focusing optic, you've got those losses. Sometimes an OEM will calibrate that at the resonator to kind of offset that, but usually what I've seen is that they don't do that, and that's why it is so very important to take the measurement at the workpiece. Another question that came in is how the focal position of the laser beam will affect the welding process. That's a really good question. I will say that neither Dick or I are really per se experts in laser processes or laser applications as much as we are experts in laser measurement. So I can't really very informatively answer that question, but I will tell you that why it's important to measure your focus spot is that you need to know, number one, how much power your output, and number two, how large your focus spot is, because as I mentioned before, for the same reason that you can put a hole through your power sensor, that power density is really what you're trying to measure, is how much power and how small it's being focused down to. So I can confidently tell you that the differences in the power density will affect your weld. But as far as how the laser interfaces with the weld, there are different power densities that you need to calculate for different materials. I know that you need to do that. I can't really intelligently talk about that today, but it is a really good question.
One last question.
I think we're at the top of the hour, so if we have time for more questions.
Do we have time for one more?
Yep, just one more question.
Okay. The other question that came in that may be interesting says, can the water-cooled sensors lose precision because of the water cooling temperature, pressure, and flow? And the answer is yes. They won't change immediately, but over a period of time, 30 minutes to an hour, if the pressure is different, if the temperature of the water begins to change, if the flow rate is different, it will affect the thermal stability of that sensor, and at some point your measurements are going to drift one way or the other. Typically with most water-cooled thermopile sensors, there is a specification, Ophir certainly provides one, as to what constants need to be maintained relative to flow and temperature. And if that can be maintained, and typically they're not that stringent, but if they drift significantly, then the readings will change proportionately. That's correct.
Okay, great. All right, well, I think that concludes our webcast for today. On behalf of Industrial Laser Solutions and Penwell Corporation, I'd like to thank today's speakers, John McCauley and Dick Riley of the sponsoring company, Ophir Spiricon. And please join us for our next webcast on July 25th, where Ron Schaefer from Photo Machining will update us on laser-based medical device manufacturing. So thank you very much for attending.
Thank you.
Thank you.